Dr. Murthy, how do we approach classification problems when there are more than two possible classifications?
This time, I don't have a um, binary classification. I have a multi-class classification. So I want to now give a lot of information about a patient, whatever four attributes. Let's say they have temperature, they have a throat ache, their whatever blood test yielded these results, and now there are three possible results. The guy can be healthy, the guy can be suffering from COVID, the guy can be suffering from flu. I don't know which one is which. So now you see the power of neural nets nicely. I can represent it. It's very, very sweet that way. Now, exactly the same way now I connect from every one of these guys. From first node, second node, third node, all connect to. So you can think of these as W1, W2, W3, W4. I have one regression problem. Now, I will now define another regression problem where I connect all of these to this node. It'll just get ugly, but I will just draw. Let's see, I can draw a dotted line this time. They are not weak or anything. I just don't want to. I want to represent them differently. And in fact, you know what? I am going to color them also differently. Cool. This is the second set of weights. You can think of this multi-class classification as multiple classification problems are solved at once. Like that, I have to connect for the third guy also. This time I will use even more. No. This time I will use even more finer thing, and this time I'll use black. Okay, no confusion whatsoever. Okay. So you see, when I have a multi-class problem, my representation is connecting like this. Nice and clean. I call the first weights W1, W2, W3, W4, and then so let's say I call these weights the dark guys. Okay. Oops. This blue guy, this guy has to be in blue also. This blue guys, I can call them W1, W2, W3, W4. My mom would be so happy to see this. My handwriting was never this beautiful. Okay. This time the red guys, this is not the most standard representation, but there is a reason why it's simpler, but I will introduce you to a different style once we do the later lectures. But for the time being, let's call the red ones K1, K2, K3, K4. K2, K3, K4, and finally black guys. H1, H2, H3, H4. Right. So now I have 12 weights as X. In fact, no, I made a mistake. I need to have the bias for each one too. So a B1 here, a B1 here, and let's call it B1, and I'll not draw the other guys. It's obvious. So the biases are then B2, B3. So let's get the bias terms, B1, B2, B3. Let's get the math here. If I have four inputs and three outputs, I will have 4 times 3, 12 connections plus 3 biases. How many ever outputs are there? That many bias terms. So the total number of unknowns in the system is um, number of inputs I n plus times number of outputs O n. This is one component plus OM. How many ever outputs are there? I combine, I will have that many bias terms. So in my neural network representation of a multi-class classification, this is a perceptron, this is not a complete. There are more complex neural networks. We'll talk about them later. But um, this is perceptron to solve a multi-class classification. So um, in times on, that is 4 times 3, 12 plus 3. 15 variables I need to solve, weights I need to solve, and biases.
Oh, that is one complex perceptron, Dr. Murthy, with far too many unknowns. I cannot even begin to imagine how to solve this problem. I guess that's where AI enters the picture. Thank you for the lesson.